Yeah. So again, hello to the round after the long lunch break. My name is Michael, and yeah, laser pointer works too. So I'm going to do a quick and short presentation on some non-scientific but still hard implementation work, I think. The title is a new 802.15.4 simulation model for OMNeT and INET. Christoph gave me a bit too much credit here with a new. It might be new, but it's also old in the case that we have previous models and we had some models to look at and took some parts from here and from there and combined them into a new model. I also would like to call it yet another IEEE model. Yet another because 802.15.4 has a long history with OMNeT. I think the first model came out in 2007. During the years with the different frameworks, we had 5 or 6 different ways to model 802.15.4, 5 or 6 different implementations, and yeah, this is yet another one. So with the title, I thought that many people had different questions coming up, so I tried to answer the basic ones for introduction. The first one would be, what exactly is this 802.15.4? People that don't work in the sensor network area maybe don't know this standard. It is essentially data link and a physical layer for low power, low transmission range, low energy networks, wireless personal area networks. So the standard defines like the PHY layer, the MAC layer, some service adaptation layers for higher logical link layer controls. And it enables us to have wireless communications for sensor networks, embedded systems, this ominous cyber physical systems wave that's coming over us. So that is basically what is 802.15.4. And next big question would probably, why do we need a model for this? It is actually a proven standard. We have implementations for this. We have physical transceivers that we can buy and use in everyday applications. Sensor nodes are, well, still not very common, but at least affordable. So why do we need to model it? It is still the de facto standard for Internet of Things scenarios until Wi-Fi becomes even cheaper and even more low power than it is today. Many people, researchers and developers alike, still use 802.15.4 for Internet of Things applications. And Internet of Things for us is still the interconnection of the physical with the digital, the virtual world. So bringing the virtual world with the physical world in one combination, in one integration, one environment. And what we actually look into is the bigger picture here. What we try to achieve with OMNeT is bring together different models for different standards and try to simulate Internet of Things scenarios. So that's the basic long-term goal that we have. And for this, we actually need 802.15.4. We need something like 6LoW vPAN and IP version 6. For those who don't know 6LoW vPAN, it's IP version 6 over low power wireless personal area networks. It's one of the longest acronyms we have in internet and embedding world. I used to call it like the glue between the embedded and the desktop world. IP version 6 is what unites both worlds in terms of networking. It's the common internet protocol layer that we use and that we can use in both worlds, that enables us to do direct end-to-end connections between sensor nodes and internet-connected nodes, desktops, mainframes, whatever. And 6LoW vPAN provides this adaptation of the large IP version 6 protocol to the small and resource-constrained world of sensor nodes and 802.15.4. Bless you. Okay, then the next and the most important question would probably be, why do we need a new model? There are so many models available. I try to answer this by going back into the history. Actually, the first model that was available is the second that I listed here. It's the 802.15.4 model from Feng Chen and Falco Dressler. It was developed back in 2007 to 2008. It was a big cooperation project with Siemens back then, I think. And it was based on an NS2 model, partly conformed to a certain revision of the standards. NS2 model was the ancestor of all simulation models of 802.15.4, came out in 2007 and 2006-07, and this model had support for many things that the standard specifies, many MAC operations, service primitives that are specified, things like super frame and guaranteed time slots. There were certain things missing, star topology things, yeah, only beacon management wasn't considered, PAN management. For that time period, it was okay. People didn't use those services or didn't want to research on these topics. It was okay. A bit later out was Castalia framework with their implementation. Castalia framework, for those who don't know it, it's usually a framework that you use to do lower layer simulations, physical layer simulations, and personal area networks, body area networks. So things like health application sensors that you use on your body, and you want to simulate the way that they communicate. Please join me. Okay, Castalia has a large focus on the physical layer, so they are very good at modeling physical layer phenomena and physical layer transmission effects. They didn't care actually about the MAC layer and the higher layer functionalities of 802.15.4. So, of course, whenever you develop a model, you have a specific application background in mind, and theirs was just the physical layer. And if you ever work with Castalia, well, it's a bit hard to do live debugging, live working with it, because they completely omit the GUI. So it's just you do command line simulations, get your results back, have something like a trace file that you can maybe look into, and the results. But if you're developing the model or working with different models together, it's really hard to do it with Castalia. Other frameworks that came later, Mixum framework, their 802.15.4 implementation that was actually ported from the mobility framework, which was one of the basic founding frameworks to go into Mixum. They also had an extensive physical layer and an extensive radio model. But again, the MEC layer was a bit, it was this child that you never feed. So certain things were missing, much more things than in Feng Chen's 802.15.4 model for INET. And the latest and greatest is from INET MANET's framework. There's a part of the 802.15.4 model for the normal INET framework, but it's not complete. And they also took the at least the CSMA-CA model, so collision sense multiple access model from 802.15.4 and used it in the INET framework. So actually, based on those decisions, we came up with the idea, it's not really research type, but practical type. Let's learn something, let's create our own model, let's do it in our own ways and combine the lessons that we learned from looking at the existing models. It is probably nothing that we would go up for a conference, but it's the beginning for developing a model that might combine things that are already there into a bit more usable form, into a form that can be used with the current version of INET, the current version of OMNeT, and that might be a good standard for doing additional research, doing additional developments on. So let's take a short look. I try to keep this really short, no look into the source code and anything. This is the abstract way of how it looks like when you take the model now and try to use it. So we try to keep it in a way that it's very similar to using standard INET models and to like keeping it next to the form of INET's 802.11 implementation. I think many people used either the Ethernet model or the wireless LAN model from INET, and they're quite familiar with the way how to interact with it and how to use it. So we also try to keep this together, like with using standard host things, keeping things like the NIC, network interface card, like it is divided in INET MANET, which I think is quite nice. It resembles the way that we would program and use it in real life with real devices. Of course, the NIC divided into MAC and PHY layer. What we also see here, the network layer, the normal 802.15.4 standard doesn't provide any routing protocols, any network layer operations. And this is here the naked model itself. So there's no routing and there's no IP and nothing. This comes with other additional models. What we have is some standard link layer control and some service-specific convergence sublayer, which just provides some adaptations for higher layers, application transport layers that do not understand 802.15.4 service primitives. And when we go down in the MAC, there's just a normal MAC model and some buffer module where we enqueue packets. We found out in real implementations that they have a similar buffer there in certain modules. Sometimes it's a hardware buffer, When the Mac is written in hardware, sometimes, or usually it's just software, so we also incorporated this. The PHY we actually split up into a radio interface and a real radio. This was way before the PHY layer redesign of INET, so we tried to keep it like 802.11 does it. Yeah, abstracting the radio and try to use most of the 802.11 radio implementation. And we'll see in the next talk how things will work out in the future, and yeah, adapting to this is also one of our future tasks. So what we actually have at the moment, this is a short overview of the basic functionalities. Many things are like, you know from other simulation models from 802.15.4. So we support different device types, different transmission and network types, things that weren't there before in INET, 64-bit MAC addresses, which is quite important for newer wireless communication models, since those 84-bit MAC addresses, they are quite they're common for Ethernet, but newer wireless devices, Bluetooth devices, 802.15.4, Zigbee things, they usually use like 64-bit MAC addresses, so yeah, we have to get that into INET. MAC functions were quite complete here by relying partly on Feng Chen's model for the carrier sense multiple access part, which was done quite nicely. We extended it with the beacon and PAN management things. Still, there are some open questions regarding the superframe things, because when you work with a specification from IEEE, they usually leave out the interesting parts. So they describe all the standard things that you can imagine, and when it comes to how does this tricky magic works, oh yeah, it's up for you to decide. And, so we also had some problems with ambiguities in the specifications, still ongoing problems. The PHY is basically this 802.11 model that we enhanced with additional things that we just need for 802.15.4, namely energy detection, clear channel assessments, so just the way to decide if the channel is free or not, or energy detection is how many other peoples are operating on the same channel, things like that. And this is new that other models didn't have, this cervic conversion, cervic specific convergence sublayer, just a way to adapt to higher layer protocols whenever they don't understand those service primitives that we operate on the lower layers. So we strictly kept to the standard and not abstracting any of the service primitives. So whenever you touch the model, you will see that there are many, many messages generated inside and service primitives exchanged between the different layers. For example, when you want to start a transmission here, there's probably around 20 to 30 service primitives exchanged before, if it's the first transmission, because the standard just does things like, okay, setting up a personal area network, deciding who's the coordinator in this network, depending on the actual type of network, sensing the channel, things like this. And we try to stick to the channel, to the specification here, and model all those service primitives. So that's why lots of messages generated. It takes a certain amount of time. While other models just abstract this, and they just like, okay, channel is free, let's send. But if you take a look at real implementations, real devices, those things happen. They stick to the standard. And I'll come back to this on the long-term goal. Because for us at the moment, the question is, where do we go now from here? We have basic implementation. Well, it's not completely tested and far from error-free. So we still need to do lots of more testing and lots of more debugging, especially if you take the other things into consideration. Very important for us is that we provide some full integration into INET. At least for me, I think that people will use models more if they are combined into the bigger frameworks, like in Vanes, or even when Vanes gets integrated into INET, when we have like this one central catalog of models. And things that are supported inside INET, that are brought up with INET, I think people will use them quite often. Instead of just, oh yeah, this is my model, just use it as you like. It's not officially supported anymore, but you can take it. And things that are integrated into INET, they receive official support, at least a better support from the community. So we try to do it and to get it integrated into INET. Yeah, next best thing would also be to migrate it to the new PHY layer. Well, we're going to hear in the next talk about this unified, scalable, and extensible physical layer net design. more interesting for research is actually the next two things. Those are just implementation things. We try to interconnect it with Sixlo VPAN simulation model that we have and INET's IP version 6 simulation model. Just to have a basic operating sets, basic tool set to simulate Internet of Things scenarios with INET and with OMNeT. And we also try to enhance model accuracy in a way that we want to profile the operation runtimes on real devices and migrate those times, those spend times, those profiles into the simulation model. And that's why we kept to sticking modeling all the primitives. Because like packetizing things, exchanging service primitives on real hardware takes real time. And in the simulation, it doesn't take any real time. If I just send a message from upper layer to physical layer, things happen instantly without any time that passes in OMNeT. In real time, of course, this takes time, especially when we go into the embedded world. Things might take a couple of milliseconds there, and it's quite some time. For this, we might refrain to use the Horizon framework, which is also from RWTH Aachen, and they have an interesting way of integrating operating times for specific operations. For them, it was more to do parallel simulation, as far as I remember. For us, we try to look into it as to enhance the accuracy by using the approach that they have.
But I think is that would maybe get parallel.
Maybe, yeah, but parallelization for us is like, okay, we don't touch that. Okay, and smaller here, some additional features, maybe it would be nice to have some things like security support, support for new file revisions that weren't there. It might leak back to this point here, depending on if we have time and if we have the capabilities to provide some input maybe for the physical layer redesign, to provide some new physical layer models, then we could also maybe extend the PHY. So the long-term goal, that's actually what the community might be interested in the long term, is that we can simulate Internet of Things scenarios. There are other simulators, more like simulators from embedded applications, from the embedded area, like Contiki and Koya, or Kuja. They already provide Internet of Things simulations, but in a very small way, and also just in a way where the sensor network itself is the center point of the simulation. But if we look into the real Internet of Things, there's always some system that is connected to the internet, and there are things happening in the sensor network, and there are things happening in the gateway that connects me to the internet or to some wired connection, and then there are things happening in the backbone and in the internet itself. So this is where OMNeT, from my point of view, comes in, because OMNeT already provides the desktop world, the internet world. And those embedded hardware simulators, they never touch this area. They have no clue what's going on after the gateway. They just simulate, pretty accurately simulate what's happening inside the wireless network, inside the sensor network. But if I want to combine a sensor network, a gateway, and some backbone in the internet, well, that leaves me pretty much with no option except for OMNeT, from my point of view, and commercial software. But in the open source software world, that's where OMNeT comes in. And our long-term goal is, we have this side here in OMNeT. Well, we provide this side here, basically this one too. Maybe in the future, models for those compressed stacks that we have in the embedded world, like micro IP. Plus, maybe not we, but other people providing application models for CoAP, MQTT, XMPP, other protocols that are being used in the Internet of Things scenarios. So this is what I think the long-term goal is, what stands behind developing or unifying those existing 802.15.4 models into a new one and providing a good basic subset. So that's it. So in conclusion, sooner or later there's a new model on the market for 802.15.4. It should be compatible with new INET and hopefully with a new physical layer. It will be hopefully a big next step for the simulation of Internet of Things scenarios with INET and with OMNeT, if a couple of other things that are on the way will be finished. Yeah, that's for me, and yeah. I'm happy to answer questions. Code will be on GitHub as soon as I don't forget to push the branch. So, thanks a lot for your attention.
We have 5 minutes to spare. Thank you for questions.
I try to keep it short.
I have a question about testing. I mean, you mentioned that it's still untested and so on, but I guess you plan testing. And I mean, those who have worked with real 802.54 and similar radios know that, I mean, this is the most fragile and whatever special type of scenarios you can imagine. Do you have any specific like strategy and specific model you test against? Do you have any idea how to really perform tests that give an answer on whether there's any realism in the model?
Yeah, so at the moment we're mainly doing functional testing, seeing that operations that are specified in a standard in a specific way work the same way in the model. That's the first thing. And the second thing is we try to do like interoperability tests by hooking up real sensor to the computer and trying to exchange. We're doing this over a bit certain amount of tricks at the moment, like hooking up a sensor bridge that records in PCAP, and on the other end we have the simulation model that outputs PCAP files, and the sensor bridge sends those PCAP packets back in the real network, and we see if packets come back. So that's the second way of finding out if it's a bit like this gold device tests. You bring your gold device into the test house and they see if they interoperate. So we try to get in this certain area like this. See if the model would be able to test and to work with a real stack. So, but performance tests, so this is more on the functional side from my point of view. Performance tests.
No, the question was more on the functional
Okay,
side.
yeah.
So it's also about it's also a high-level question about the testing aspect. So you don't do any human testing at all.
From the source code point.
Yeah, like you know you have a specification how things should work, and you could write unit tests, for example, that, or you could also develop in a test-driven fashion. Because you emphasize so much on the testing thing, and I was just wondering why somebody was doing unit tests in the simulation.
I might, for certain parts, I think there have been unit tests. For parts like CSMA-CA, like the algorithm itself, it might be an option to use a unit test because we have a quite clear specification for it.
Yeah.
For other things, we could maybe break it down to use unit tests for specific scenarios or even parts of the code. Probably we should use unit tests or better ways of testing to make it a real stable model. I also have to ask how other like more experienced modelers do it, so to get some feedback. So maybe tonight we can answer this question more in detail, and then I can get some feedback from myself. So yeah. Yeah, please share with me.
If we're not running out of time.
Oh, I think that's fine.
So you said a couple, so I suppose didn't want to bring up performance, but if you're actually modeling all of the internal service primitives as OMNeT messages,
Yeah.
aren't you taking wider performance hits? Have you compared it just, I wouldn't know for sure, but I can guess that would be a factor of 3 or 4 slowdown because you're just going to be generating so many messages for every operation, and OMNet's going to have to handle them. Have you compared it just even roughly?
It is, I don't have a real number, but like you described, yeah, it takes some time. And
Factor, can you say it a factor of 2, factor of 20?
well, I don't know.
Do any order of magnitude sort of, there's many.
Well, I don't know any real factor for this, but like I said, I'm not looking into like routing performance, because when we look into the type of communication that 802.15.4 provides, it's not the high performance that we're looking into here. So it doesn't make any difference if the packet takes 0.02 or 0.03. And the time that the real time that it takes to send the packet is still quite long when compared to the time that it takes for OMNeT to model this. So the execution time of the simulation, I don't care about the execution time of the simulation as long as the time that is spent, the simulated real time, is
Right,
anywhere
you
near.
obviously care about the simulated real time. I was just because if you start to want to put more CPU into modeling wireless, which is hard. I mean that's modeling the physics rather than the software. I'm just curious how much, if you had some sense of how much you were losing, because if you wanted to put a lot more into the wireless, which is really the hard part.
Yeah.
To model.
Well, we have to see. I don't know. I don't have any idea yet.
You just get a faster computer. You get a faster computer and you use extremely cool parallelization and everything's okay.
Maybe, yeah. I don't know. I mean,
this
this is.
You must be generating an enormous number of all-time messages.
It is, yeah.
To model the primitive MPLE and MLE and
Yeah.
they just do it's a lot of.
But it's at the moment it's the only way for us, for example, to have like how much time does this consume to exchange between the different layers. It's the only way to use OMNeT messages. If we do a real C++ layer calls, then it's out of OMNeT scope and we cannot model it anymore. We cannot measure it, cannot edit it in any way. And
That's true. You could probably force an internal delay in a single internal delay rather than all the messages. Because
Yeah.
I understand.
But in this case, I mean, like when we go back to this horizon approach and we give the exchange of messages a certain amount of time, that like it would take in real life, like this application call or like packetization delay, things like this. Yeah, so the real simulated time is the thing that is most important here. Execution time is the second thing. I don't think that it takes like in Sumo 2 weeks to simulate 100 seconds, something like that. But it's usually slower, definitely slower than other things. That was my call.
Okay, perfect. We're back on time. So this is all